This is going to be homework 3, part C, in which we're going to find the Q total from each part of the Carnot cycle. And to start, this is what we have from before. Is we found that our Q rev for an isothermal expansion and compression is going to be equal to this equation. And then for an adiabatic compression or expansion, it will be equal to this. So I'll start by drawing a very simple thing here. So we have our PV, and we'll start with 4 points. We'll label these A, B, C, D. This is going to be our T hot, and down here will be our T cool. So to get the total heat from this cycle, we're going to need to sum up all the individual parts of this graph. So the first would be from A to B, which would be an isothermal. So that would look like our Q would be equal to RT ln of VB over VA. From B to C, this is adiabatic. So we will have our TC in this situation, TC over TH, to the CV over R is equal to V1, which would be VB over VC. And then our next would be from C to D. So C to D, Q is going to be equal to RT ln R V2, which in this case would be VD over VC. And lastly, we have our A to D, and in both of these, our Q is equal to 0. For A to D, B to C, then we'll have D to A, in which we'll have our TH over TC, CV over R is equal to our V1, so VD over V2 or VA. And that is how we would calculate the total heat needed for one cycle. So if we were to calculate the total work done here, it would be from our Q's. So A and D and B and C would not account. So it would just be our QH and our QC. So we'll have our work is equal to QH plus QC. So our efficiency would be equal to QH plus QC over QH. So to find what our maximum efficiency would be, if we were to consider things like friction to be 0, we can move around some of these things to make this a more simplified, straightforward equation here. So as you can see, we have our TC over TH and TH over TC. So if we were to flip this around to make it TC over TH, that would also flip this around, meaning this side would be equal, and then the reciprocal of this would be equal to that. So we'll start with that. So VB over VC equals the reciprocal, so VA over VD. If we were to multiply this out, we get VB times VD is equal to VA times VC. Now if we divide by the other one, we can get VD over VC is equal to VA over VB. So this VD over VC shows up here, and we can notice that A and B are also present here. So if we were to flip this again, or take the negative log, which would also cause it to be the reciprocal, we could get that. Where do I want to write this? We'll just go here. So we'll go QH is equal to RT ln of VB over VA. And then our QC is equal to the RT ln of VA over VB. However, if we make this the negative log, these would switch, meaning we have VB over VA once again. And now, if we were to plug in what we have on the right side of the equation for our original efficiency, it would simplify. This should be TC. It would simplify down to TH minus TC over TH, or 1 minus TC over TH. And this would give you the maximum efficiency, or how much work you could get out of your engine for the amount of heat you put into it. So an example of this would say your TH is 1000 kelvins and your TC would be 500. So you would get 500 over 1000, or your maximum efficiency 0.5 or 50%, meaning you would get 50% of the energy back you put into it as work, if you were to disregard factors such as friction, which might in reality make these numbers lower. For part C, entropy is motivated or driven by the Carnot cycle in one particular way that kind of makes a lot of sense to me. But as we know, ds is equal to dq over t. So a small change in heat would result in a small change of entropy. And for the Carnot cycle, we know that the total change in entropy is equal to 0. And since both, we'll draw our diagram again here. A, B, C, and D. We know that D to A and B to C are adiabatic, or their entropy change would be 0, meaning the total entropy of the Carnot cycle system would be equal to Q hot, or A to B, so QH over T, TH plus our Q cold, so QC over TC. And since the whole cycle is equal to 0, and these are both equal to 0, we know that this must also add up to be equal to 0. And from what we just learned, that means, so this would mean our QH over TH is equal to the negative of QC over TC, which, as we know, these are essentially opposites of one another in terms of entropy, meaning they would cancel out, making it 0, supporting our definition of entropy. For part D, we're going to start with a couple equations here. We have our first law, our second law, equation for G, our enthalpy, and our entropy equations. So first start off, very simple. We just multiply the T from our entropy equation across. So TdS is equal dQ. Then we'll switch to our enthalpy. So H equals U plus PV. If we were to differentiate this, we get DH equals DU plus PdV plus VdP. And using our first law, we can substitute in our du. So dH equals dQ minus PdV plus PDV plus VdP. These two cancel out, and we'll replace our dQ that we just got. So we get a dH is equal to TdS plus VdP. And then from our second law, we have our ds of system plus our ds of our surroundings is greater than 0. So knowing this, our ds from our systems would be equal to the negative ds of our surroundings, meaning you'd end up with an equation like this, ds minus, we'll substitute in this for ds, dq over t is greater than or equal to 0. And from this, we'll multiply the t over again. So our TdS minus dq is greater than or equal to 0. And if we rearrange this, we get our dq is equal to du plus pdv. However, it's still minus here, so we'll multiply by -1, switching the sign. Plus minus, this is switched. So we'll end up with du plus pdv minus tds is less than or equal to 0. So we know that in this situation, our pressure and temperature are both going to be a constant, meaning it's the same whether they are inside or outside of what's being differentiated. So we can throw them in and just take the d out using some simple calculus rules. So our d plus u plus pv plus ts, minus ts is less than or equal to 0. And as you may notice, h is equal to u plus pv, which we have right here. H minus ts. And if you were to notice once again, very observant, we have our g is equal to h minus ts. So our dg when our pressure and temperature are constant is going to be less than 0.